Okay, assalamu alaikum, and hope that you are all doing fine. Today we are going to talk about motor controlling in using an embedded system, and basically we are going to discuss the DC motors and how we can control both the speed and the direction of the rotation. So first of all, you all know the basics of DC motors. It's a rotating shaft with a fixed of two pair magnets. It's quite a simple idea, and if you use the right thumb rule, we can know that the direction of the force is perpendicular to both the magnetic field and the direction of the current. So this basically helps the motor to start driving, and the force on the wire is perpendicular to the magnetic field and to the direction of the current through the wire. The direction of the force is determined by the left hand rule, and you can see here that we have our two magnets. This is the first one and this is the second magnet, and these are the equations for the force and torque. You can see that the torque is equal to the force multiplied by the lever arm, and which is basically this equation. The force on the wire introduces a torque about the motor shaft. The commutator switches direction of the current every half cycle. The direction of the torque remains the same throughout the full cycle because we have these connectors that keep shifting every time, and you can see that this is very important. The average motor torque is proportional to the current flow through the wires and has the same the wire has the same resistance. So as we increase the current, we basically we will get more torque. Now if you relate to this, if you have a small toy for your brother and a car, let's say, and you put batteries in it, if there are new batteries, you will find that the car is moving fast. Now if the batteries are becoming old, then they are producing less voltage, mainly less current, because the power is equal to I V, and for that the car will start moving slowly because again the current flowing is slow. Now the direction of the current flow basically determines the torque direction. We can flip the direction of the movement of the motor by changing the direction of the current. Now, how can a digital input control the torque magnitude? We use pulse width modulation. And then how we can handle the direction? This is basically handled by changing the direction of the current. So we have the 3.3 volts to north, 0 volts to south, and we have 0 volts to north and 3.3 to south. This one of them will give us clockwise and the other will give us counterclockwise. How do we implement this on a microcontroller? Okay, so how do we implement this on a microcontroller? We can get the 80 mega, and let's try to do it very fast. We will go to the Protos. I will start a new project. I will do it quite fast. Okay, and I will call it motor control. Now in this motor control, next, I will choose the 80 mega AVR, sorry, I will choose AVR, and I will choose 80 mega 16 with AVR. Next, finish. Then I will go to the code. Inside the code, I will choose quite simple code. I will say that DDR A is equal to DDR A is equal to 0x FF. I will choose output port A as an output, and I will put on port A while 1 I will say port okay, I will say port A is equal to 0x 01. This means that the first pin is 1 and the rest are zeros. So this will guarantee that the voltage will be high at port 1 port. So I will go back to my microcontroller and I will be concentrating over here on port A, which is these two pins. I will connect my circuit to them. So basically I will just go and choose a motor. This is a brushless DC motor, so which motor we are going to choose? This one is basically a simple DC motor. Okay, this is a simple DC motor. I will choose it here and I will put it here, and then I will connect this pin over here. Let me fix the connection so it looks nice. So what I did here is I connected pin 0 to one port and pin 1 to one port. When I switch this circuit, okay, when I switch this circuit, okay, I got an error because I don't have a semicolon here. Okay, so I'll go back to my circuit once more. When I switch the circuit, I am going to get this output. It's very, very, very slow, and it's not enough to move the motor. You can see here. Why? Because the microcontroller does not have enough power to move this motor. It is moving, yes, but as you see here, this is a gray. Gray means not enough power. Okay, it's not high or low. If it's low, it will be blue. If it's red, if it is high, then this one is supposed to be blue. You can see here that we cannot drive a motor from a microcontroller. We cannot drive a motor from a microcontroller. Then how do we drive a motor from a microcontroller? In order to drive a motor from a microcontroller, we need to think more about that. So first of all, you can see here that if we connected this connection, we are not going to have the implementation right, because the input output pins can only source or sink 10 milliamps. Okay, these ports can only source or sink 10 milliamperes. This is not very much when it comes to motors. Then how do we fix this problem? We fix it by an NPN transistor. Now this NPN transistor, as you all know, if I put +5 over here, the transistor will be on and current will flow from the collector and base to the emitter. If I put 0, then VBE will be equal to 0, and we are not going to have any current because the motor will be off. So the current from the base to emitter is non-negative, and small base to emitter currents open the valve or the transistor so that the current from the collector to the emitter can start flowing. So you see here, if I apply 0 volts, which is logic 0, it will have no volt because the transistor will be off. But if I put 1, then the current will start flowing, and current will start flowing, more current will flow over here. Remember, IC is equal to beta IB, and beta, I don't know why writing like this today, and beta will equal to around 100. So whatever goes here, it will be multiplied by around 100 or 150 to get the collector current. Now let's apply this over here. So if we apply 1 here and 1 here, then the current will flow through the motor to the ground, and the motor will rotate in this direction. And if we apply the other 2 transistors, the motor will move through this over here. Now, what happens if we apply like this? What will happen? I is equal to V over R. R is equal to 0, so I will equal to V over 0, which is infinity. And in this case, you are going to burn your circuit. You're going to have a short circuit and you're going to have some problems in your circuit. So here, instead of having to control 4 transistors, we can control them only through one input. If I put 0 here, what will happen? 0 here means that this input is 1. Sorry. Means this input is 1 and this input is 1. And if we put 1, we get the other 2. And here we solve the problem of having a short circuit, because we will never have the case where these two or these two are working together. We will not have that case at all. This implementation is nice because we only need one direction bit of control. So what is missing? We need to control the speed of the motor. We need to control the speed of the motors. To control the speed of the motor, we need to discuss pulse width modulation. Now, in order to discuss pulse width modulation, let me go back here. Over here, any digital signal is represented by amplitude and frequency. Okay, everything is controlled through amplitude and frequency. Amplitude is basically the voltage over here, and in digital circuits our amplitude are either 0 or 5 volts. But when it comes to frequency, all of us know it is the total period, which is T low and T high. Okay, T low plus T high. So T, the total time, is equal to time low plus time high. Now, combining this together, we will get the frequency is equal to 1 over T. Now, the duty cycle, now the duty cycle is equal to time high over time high plus time low multiplied by 100%. يعني it is the ratio of the time high to the total time period. Now, how does this relate to our work in computer systems? Now, in a microcontroller, okay, in a microcontroller, just give me one moment, okay. In a microcontroller, if we have a motor, okay, if we have a motor that is driven by a 5 volt, it will go always maximum speed. Now, if I have a motor which is driven at 0 volts, it will go 0 speed. Now, assume that I'm trying to drive my motor, okay? Assume that I'm trying to drive my motor, I can work here, at something like this. My motor, it's like playing with the car, switching on and off very fast, on and off very fast. Then you will end up, if my duty cycle is 50% and I'm running my motor for duty cycle 50%, this means the time high is equal to the time low, and I'm going to get an average of around 2.5 volts because of switching on and off. So if I increase my duty cycle to something like, if I increase my duty cycle to something like, let's say 70%, if I increase my duty cycle to something like 70%, this means 70% of the period high, 30% low, 70% of the period high, 30% low, 70 high. This is for duty cycle equal to 70%. So this will give us again, this will give us an average of around 0.7 from the 5 volts, which is around 4 something volts. So I will get higher voltage, okay, around 4 volts maybe. If I check, it's around it's 0.7 multiplied by 5, 3.5 volts. We will get a precise, okay, we will get a precise 3.5 volts. So this is the idea, okay? So if you increase the duty cycle, we get higher voltage. If you decrease the duty cycle, you get lower voltage. This is how you control the speed of the motor. This is how you control, this is how you control the speed of the motor, as you can see. Now, that being said, the goal of the pulse width modulation is to switch on and off the input very fast so that we get an average torque on the motor. We get an average torque on the motor with a high frequency signal. So the inertia of the motor smooths out the sharp on and off transitions. What do we mean by inertia? The inertia in Arabic هو عزم القصور. Okay, so if your motor is having zero inertia, يعني no inertia, you power it on, it's on, you power it off, immediately stops. You will have an output, okay, you're going to have an output which will be something like this. So assume that again once more, this is my output. My motor is running 5 volts, and once I power off, the motor speed will go 0 because inertia is 0. Then I will go high, motor, then 0. This is not practical, and this is not actual, because each object has an inertia. Now, on the other hand, if I'm using a motor that has some inertia, okay, if I'm using a motor that has some inertia, then I'm running 5 volts, I power off, the motor will start decreasing, then the motor will start on once more, then the motor will decrease, then increase, then decrease, and so on until it smooths out at an average speed related to this on and off of the frequency. This is the idea, okay? This is how it's implemented using the moments of inertia for a motor. So with a high frequency signal, the inertia of the motor smooths out the sharp on and off transitions. So in order to do that, we have 2 inputs. One input for the direction, the other input is used for the inertia or for the speed. So if I put 0, and remember these are AND gates, 0 means 0 here and 0 here, so nothing is working. Now if I put 1, the output depends on X. Okay, the output depends on X. So this is X complement and this is X. So this, if it is 0, then this is 0, this is 0, this is 1, this is 1. The current will be flowing in this direction. Now if this is 1, the current will be flowing in the other direction. And this input will control the speed of the motor. So this signal is used for the speed and this signal is used for the direction of the motor. So we use pulse width modulation along with the direction to control the motor that we are using. Now the H bridge in more details. Of course, this configuration is called the H bridge, and it's called the H bridge for a simple reason, because if I use my highlighter, if you see, this is the letter H. That's why it's called the H bridge. Now, remember, when a motor is moving, okay. Remember, when a motor is moving, what happens? What happens is the current is flowing through that motor and rotation is happening. If I remove the current from the motor and the motor still is moving, it will work as a generator. It will start generating current. So the diodes across the transistors are connected upwards. This is just to protect the circuit. Why? Remember, if the voltage is going through here, this diode will be off, so no problem. It will go here, it will go here. This diode will be, this diode will be off, and so on. And of course, these will be, all the diodes are off. Now, once all transistors are off, but the motor is still spinning. Yani, I switched off all the transistors. We gave 0 to the transistors. We want the motor to stop, but the motor is still spinning. This motor will start pushing current. Okay, this motor will start to push current. In order to control this pushing of the current, the diode will move that current to the power supply over here. The diode will move the current to the power supply over here in order to protect the circuit and at the same time to stop the motor. Also, the top transistors of the motor is spinning, the top transistors are on. We will have some circuit like this, and the current moves through the diodes in the left, then through the diode on the right. This will slow the motor by itself. The motor will be slowed by itself, and it's like breaking the motor by using its current. Now, the H bridge that we use is basically this H bridge, and this H bridge is very commonly used. It can control 2 motors at the same time. It has enable, it has direction, and it has 2 output ports. It takes 12 volts on this port, it takes ground over here, and it takes VCC over here. So this is how it is connected. 10 volts on the motors and 12 volts as source. It uses a current mirror, and it is the L298, okay, L298 driver. So the L298 driver, if I go over here and okay, so if we want to connect the motors to the system, we want to use the L92H bridge. So remember, we are using the same program as before. I'm just going to rotate it 180 degrees. I will take input 2 to lid 0 and over here, this one, then this one here. Enable will be connected to VCC. Now we need terminals over here, so I'm going to choose power, and I'm going to put 1 power here and 1 power here. This one will be connected like this, this one will be connected like this. Now these need labels. You need to say that this is this is plus 12 volts, and this is plus 5 volts, and you need to connect your motor over here and over here. Now if I run the program, you see that the motor is running smoothly. Now let's say that I want to control the speed of this motor. If I want to control the speed of this motor, I need to remove the enable from here. I can connect the enable to a function generator. Where is the function generator? It's a pulse. Okay, connect it to a pulse here, and okay, something like this. Can double click on the pulse, and I want to say the speed of the pulse. The voltage high is 5 volts, and the pulse having duty cycle of 50%, and it is running at 1 Hertz. So I mean 1 second high, 1 second low. So if we run, we will see that 1 second high, 1 second low, 1 second high, 1 second low. You can see that the motor, how it's going slower and higher. Now I can also swap this motor to show you more in details. Here I can swap the motor with a motor with an RPM on it. I think there's one here. Here, a motor with, which one? I think let's see if this one works. Try to run. Okay, then it means that escape. That means we need to connect it to the middle one, I think, from here to here. Of course, I forgot to connect the ground here, so ground is important. Connect the ground. Try to run it once more. Okay, this motor is not the one that we want to use, so I can stop, remove it, go back to my components, try to find me another motor with a speed on it. I think there is one. This is servo, this is stepper, this is pulse width modulated servo, this is encode, this is DC motor. Okay, this one. Okay, this one should work fine. What I want to show you here is how things are controlled. So if I click and start, see here how the speed, because we are on and off with some inertia. Now if I double click on this, make it faster. See, I'm just clicking on it, making it on and off faster. Okay, so if I remove, it will go back to the 1 second high and low, and it will go slow. Okay, so this is basically the this basically is our